Hi, and welcome to this third video in the section on vectors. And in previous videos we've looked at just the basics of calculations with vectors and what vectors are all about. So now we're actually going to look at how we can use these things in a couple of different applications that you're going to come across. And the first one is geometric proofs. So we're going to have a look at geometric proofs, and then the second one we're going to look at is applications to speed, distance, time, and whole mechanics thing. You'll see later on, particularly in year 2 mechanics, vectors appearing quite a lot. So here we go, let's have a look at some proofs. So we're looking at basically proofs within particular shapes, triangles, parallelograms, etc, etc. So we've got an example here. So we've got OPQ as a triangle, and we've got T is a point on PQ such that it splits in the ratio 2 to 1. So that distance there is twice that distance there. So the first question is write down in terms of A and B an expression for PQ. So we've got A is the vector going from OP, B is the vector going OQ, and we saw this last time. We'll just kind of recap it here. To get from P to Q, I like to kind of sit down with these things first of all and come up with what I call a route map. How am I going to get along the route I want, or for the vector I want, which is that one, going along things I know. So I've got to go that way. So I'm going to write down my route, which I'm going to go from P to O, O to Q, and once I've figured that out, then it's just a simple case of looking at what these things are in terms of the vectors, and clearly PO is the minus version of that, so that's minus A plus B, and that one was really nice and straightforward. Now let's have a look at the vector OT. So it's going from O there to T there. So we need to start thinking about, well, what fraction of T, or where is it along PQ, and that gives us our ratio. If this is in the ratio 2 to 1, then this bit here has got to be 2/3, and that bit from T to Q has got to be 1/3. So just be a little bit careful. We're not talking about halves, because we've got a ratio of 2 to 1, we're talking about thirds. So here we go, OT. Again, I'm going to plan out my route, and I'm going to go from O to P and P to T. There it is, so I'm going to do OP plus PT, and we therefore want OP, which is that, and as I said before, we need 2/3 of PQ. And if I want 2/3 of PQ, well, if you have a look at part A, PQ, I've got it here, that's that thing there. So what I need is A, which is OP, plus 2/3 PQ, which is 2/3 of minus A plus B. So next job is just a bit of multiplying out and tidying up. So multiply the brackets, get all my A's together, and then you could leave it like that if it just says express it in terms of A and B, which we've done, but it says give your answer in its simplest form, and it's always useful to do a bit of factorising where possible, and you'll see more reasons for why we need to do that later on. So take out the third, and we've got 1/3 A plus 2B. Now, in this particular case, I went from O to P, P to T, but there's absolutely no reason why I couldn't go a different way. So I could go from O to T, giving me O to Q, and then Q to T, and I know that this one here is 1/3 of QP. So there's a different route, but it should give me exactly the same result. So let's have a look at what's going to happen. So OQ is clearly B. And here we've just got to be a bit careful, because in the previous question we went from P to Q. So this time we're going in the opposite direction, which is why we're going to need the minus sign there. So now we've got a minus and minus. We're just going to be a bit careful with our minus signs. And we end up there, and what do you know, it's exactly the same, which is what we were pretty much expecting. Okay, so when you look at your routes, it doesn't really matter which route you choose. Some might be easier than others. There's no particular right or wrong. But whichever way you do, as long as you do it correctly, you'll get exactly the same answer. Okay, that one was reasonably straightforward. Let's make it a little bit more difficult now. So here we go. We've got a parallelogram, and we've got some points. We're told that M is the midpoint of AC, and we're told that A is 2/3 away along the line AD. And we've got our two vectors. I'm just going to draw them on. There we go. AB is the vector U, and AD is the vector V. So we're going to want, first of all, AM, so A to M. So AM is clearly going to be half the distance from A to C. I'm going to need to figure out AC, and hopefully we're reasonably happy AC is just the same as U plus V. Notice here that BC, because it's a parallelogram, BC is going to be the same as AD, so that's why it's the vector V. Okay, it says, hence find an expression for NM, so I'm going from N to M. So again, my route I'm going to have to plan. I'm going to go from N to A, and then from A to M, and AM is the bit we already did, so we've just got to include this bit here. So NA is going to be minus a fraction of V, and so we've got the 2/3 here, so we've got minus 2/3 V plus a half of U plus V, and then it's just a case again of multiplying out the brackets and doing a bit of tidying up, and we end up with that vector there. Okay, these last two lines here, I've kind of jumped the multiplying out the bracket skips. You can figure out that it's just a question of putting your fractions together. Okay, so we've got 1/6 3U minus V. Okay, part B, on we go. So we're going from N to P. Now P's not on here, so I'm going to have a look at what the diagram says. AB is extended to a new point P. So let's put that in. And we're told that BP, this vector here, is the same as AB. So that vector from there to there is U. So we know that all of AP is going to be 2U. Okay, so once we've got all that clear in our minds, let's go for it. So again, from N to P, I'm going to go from, oh, where is it? There you go. From N to A to P. So we've got minus 2/3 V, which is that bit there, plus the 2U. Okay, so that was really straightforward. Right, so on we go to part C, and it says prove that N, M, and P lie on a straight line. And this is kind of what I'm building up to with this question, which is the proof part. And the first thing to note is just because on my diagram I can draw a straight line through there, doesn't mean that it actually is a straight line. We've got to be able to prove it mathematically. And what I'm going to do is use the previous result that we had, which is NP. So we've got that vector there. And to begin with, I'm just going to do a bit of tidying up, a bit of factorising here. So if we take out a third, we get 1/3 6U minus 2V. And clearly I can take out another factor here. I'm going to take out a factor of 2. So we've got that expression there, 2/3 bracket 3U minus V. Now, the reason that the factorising is important is because if we go back and have a look at what we had from NM, we can see from our previous one, so we've got NM, which is that bit there, is 1/6 3U minus V. So what we've got is the 3U minus V here, 3U minus V here, and this is the kind of crux of vector proofs. Because what we can say is that those two vectors, so NM, which is that little one there, and then NP, which is all of that there, both of those are multiples of 3U minus V. And so what that tells us is they're both going in the same direction. So we know straight away that NM and NP are parallel. Now, that on its own isn't quite enough to say that they're a straight line, because we've proved that we've got two vectors that are parallel, but we know parallel vectors can be anywhere. They don't have to be in a straight line. So what we're going to do is just add an extra little statement, say, well, why are these two in a straight line? And it's blatantly obvious that they are. And the statement that we're going to add is quite simply that since both vectors start at N, NMP must be a straight line. So the two bits of being parallel and the fact they both start in a place, the two bits put together means that NMP is in fact a straight line. Okay, so on we go to our final example, and we're going to prove a generic statement. It says use vectors to prove that the diagonals of a parallel bisect each other, and by bisect, hopefully we know that means just chops them each in half. So there we go, there's any parallelogram. So I've got a parallelogram OABC, and I've got the diagonals OB, AC, and we've got a point in the middle X where they bisect. I said in the middle, and I'm saying bisect. We've got to prove these things. So what we've got to do is say we'll start off by defining the two vectors. OA is A, OC is C. We've already said about the diagonals. So we know that diagonal OB is A plus C, and again the same reason that this vector here, AB, is going to be the same as the vector here, C, because it's a parallelogram. And we've also got the vector AC. Now this one clearly is going to be minus A plus C. So there's our two diagonals. And we've got the point at which the diagonals meet. And so what I'm going to say is that OX is some fraction of OB. And we're hoping to prove that for this value here, this thing K, this is going to be my fraction. And I'm hoping to prove that that's going to be a half. That's what I'm aiming for, but I don't know it's a half at the moment. I've got to prove it. I've got to work towards it. So for now, I'm just going to say, okay, K represents some fraction, so K is between 0 and 1. Okay, so we're hoping to prove that K equals a half. So OX is, let's say, a fraction of AC. Do a bit of multiplying out, and I get that. And then what I'm going to do, and this is a kind of a sneaky little trick that's fairly standard for these kind of proofs, is say, well, we defined OX by saying it's just a fraction of that. Let's think about another route we can take to find OX. So how else can I get from O to X rather than just going along AB? Well, I'm going to use the other diagonal. So what I'm going to do is say that OX is OA plus AX. And in the same way as I described OX as being some fraction of OB, I'm going to describe AX as being some fraction of AC. Now, I don't know what that fraction is. I don't know if it's the same or different at this point in time to what we had before, so I'm going to have to use a different letter. So I'm going to say it's A plus some fraction of AC for some value of M. And again, clearly I'm hoping that M is going to turn out to be a half, because that's what we're aiming to prove. So we've got our expression there for OX, which is A plus M lots of, and this bit here, this is our AC that we had before. Multiply out the brackets and do a bit of tidying up, so I can refactorise this and by taking A outside the bracket there. So I end up with an expression which is A bracket 1 minus M plus MC. What that means, therefore, is that I've now got two expressions for exactly the same thing. So if both these things are ways of describing OX, then I can just put the two things together and say, you know what, well, this one here is equivalent to this one over here. Notice I've just used kind of the equal sign with three lines to mean equivalent to. They're going to be the same for some values of K and M. Now, here comes the next sneaky trick. What I'm going to do is say, well, if we know that the two things are the same, then the number of A's I've got on this side have got to be the amount of A's I've got on this side, because if they're not, then the two expressions aren't the same. And likewise, the number of C's on this side have got to be the same as the number of C's on this side. And so that allows me to split this out and form two equations. The first equation is say, well, let's have a look at the A's. And we're saying, therefore, the number of A's over here, which is K lots of A, has got to be the same as 1 minus M, which is the number of A's over here. And if we do exactly the same with the C's, we can say that I've got K lots of C over here, I've got M lots of C over here. So if those two things are going to be the same, therefore K and M have got to be the same value. So now what I've got is a simultaneous equation which I've got to solve. However you choose to do that, I think probably the easiest way is to say, well, if K is the same as M, I'm just going to take the M here and replace it with a K, because those two things are the same thing. So what that gives me is K equals 1 minus K. Solve that for K. And what do you know? K equals a half, which is exactly what we're after. And since K and M are the same, down here I've put a note saying that M is a half as well. So what we've just proved there is that if AX is a fraction of AC, it's clearly half of AC. We're saying OX is a fraction of OB, and we're saying that's half of OB, so clearly it's splitting these things, each diagonal in half, so they are bisecting, so that's our proof. Job done.